Talked a little bit in the last video about using different kinds of energy and what that means. So now let's look at some problems from chapter 11, and then we will explain the concepts as we start to solve the problems. Okay? So this is going to be a conceptual video, but it's also going to talk about problem solving in chapter 11. All right. All right. And I do really like the book. So the book I think is really clear. I think a lot of you use the book or you read it and take notes. That's a good strategy. All right, so let's take a look here at chapter 11 and see what we got going on. All right. Uh, all right. Oh, this is a good one. I love this question. All right. If you leave a fan running, it actually warms up the air in the room. A fact that surprises many people. That is true. And here's the reason why. Okay. When you turn on a fan, that fan is doing work. Okay. The electric motor is not 100% efficient. It's going to heat up. You're also going to be heating up the air in the room. So you were putting energy into that room, which goes into creating thermal energy in the room. Okay. So the answer is yes. If you leave a fan running in the room, the overall temperature of the room is going to increase. Now, why does it feel cooler when the fan blows on you? Well, that's because your skin you're constantly sweating a little bit. You're perspiring. And so the way that it works is as your body loses those water molecules, right? They take some thermal energy with you. So as water is carried away from your skin, it takes thermal energy with it. That water has thermal energy. When things evaporate, in order to go from a liquid to a gas, that costs energy. So um, as the water molecule leaves your skin, it takes thermal energy away from your body. Okay, what is the main reason? Why would a fan be expected to warm the air that passes through it? The fan blades transfer energy as heat to the air molecules in the room, leading to an increase in thermal energy and temperature. The fan blades do work on the air molecules in the room, leading to an increase in thermal energy. All right, is it pick one? Well, I'm gonna pick this one. The fan blades do work on the air molecules. That's true. The fan blades themselves don't transfer energy as heat. They don't actually heat up. That would be really bad. Okay, so yes. All right, wonderful. We got that one. All right, let's do another problem. I like the conceptual problems. All right, let's do another problem here. Oh, what do we got? Oh, a 30% efficient car engine accelerates a 2,000 kilogram car from rest to 19 meters per second. How much energy is transferred to the engine by burning gasoline? Okay, well, here's what we need to do. All right, we know what the final energy of the car is. Okay, so here's our strategy for this problem. Okay, we are going to first calculate what that kinetic energy is. Okay, that's how much energy we're going to end up with. Okay, so you had to put at least that much energy into the system to give you that kinetic energy, but that's not all because the engine was only 30% of that energy. Okay. So, how much ever energy you have in terms of kinetic energy, okay, that is only 30% of the total energy it took to get you there. Okay. So, we live in an imperfect universe. Everything loses energy. Nothing is 100%. So, step one, calculate your kinetic energy. That's not bad. Let's write down everything that we got in the problem here because I can't the biggest number of mistakes is because I don't write down the correct information. Okay. So my energy efficiency is 30%. Okay, that's going to be important. The mass of my car is 2,000 kilograms. Now, here's another trick that I do. When I read the problem, I'm thinking, why did they give me this information? Okay, so I've got mass, I've got velocity. Okay, I know that that's probably going to be kinetic energy. Okay, so this is 19 meters per second. Let's talk about kinetic energy. Let's just write down our formula here. Kinetic energy is 1/2 mv squared. Okay, once the car is moving, right? This is how much kinetic energy you have. Now, let's think about gravitational potential energy. I mean, we're in a car on a level field, so we're probably not going to need this. Okay, all right. So basically, here's my car. Okay, here's my weird 1980s Buick. Yes, 1982 Buick. Stainless. It was solid steel. These things were absolutely massive. And they got like 15 miles per gallon. Okay. All right, so what are we gonna do? All right, first let's calculate the kinetic energy. So kinetic energy is 1/2 mv squared. So we have 1/2 times 2,000 kilograms times our velocity squared, 19 meters per second squared. That is our kinetic energy. That's when this thing is moving. And 19 meters per second is about 40 miles an hour. Okay, so when you're going 40 miles an hour. All right, let's put in the calculator here. I've got my calculator. I've got a calculator. I can calculate the kinetic energy with my calculator. So 1/2 is point 0.5 times 2,000. I'm not gonna mess up because I was really messing up the other day when I was doing this. I was just leaving stuff off. I wrote it down correctly and then I didn't enter it into my calculator. All right, so I'm gonna double check this. I got my mass. I got the 1/2. I got my velocity squared. All right, let's do it. All right, so the total number of joules. This is my car is gonna have 361,000 joules, but I'm gonna write this in scientific notation. Okay, so this is kind of crazy, man. 3.61 times 10 to the 5 joules. You have to write that in scientific notation. I can't write all those zeros, man. I can't do it. It's too many zeros. Now, this was only this was only 30% of the total energy. Okay. Um, so let's do some cross multiplying here. Now we need to find the total amount. If this is 30%, then the question is, what was the total energy that we needed for this? Okay. Let's think about it like this. Our total energy, okay? Our total energy, this is 30% of our total energy. So we're going to say times 0.30. If you're going to multiply something by a percentage, then the way to do it is you say, okay, the total energy times zero point 0.3. That's 30%, okay? That equals 3.61 times 10 to the 5 joules. Okay, so this is our equation now. This is what we don't know. Okay, so we're going to divide both sides of this here. Okay, both sides by 0.30. These cancel out. Okay, so 0.30. Okay, if I divide by a decimal, that means I'm going to have a bigger number here. And that's what I want. So I'm going to say, all right. I'm going to take my answer here. I'm going to go back to my original equation because I know that it was correct. And I'm going to say divided by 0.30. See how I just did that? I kept that equation in there. Okay. I like doing that because you know why? Because then you can see what you're doing, right? It's stored in here. I'm just going to divide this by zero point 0.3 at the end. And I'm going to say, oh, Hey, that's a much bigger number. Okay. So I'm gonna write out all the zeros with all of their glory. Okay. The total energy then is it's gonna be 1,203,333.33 joules. Wow, that is a lot of decimal places. Too many. I'm gonna write that in scientific notation. I mean, this is crazy. I don't know why I wrote all that. All right, I'm gonna write it in scientific notation. 1.2 times 10 to the sixth joules. See, that's way easier, man. And we don't need all those threes, honestly, because look, I know in the tests, all right, the significant digits were totally messed up, and I apologize for that. I am so sorry. Okay, but we're gonna do it correctly here. Okay. So this is a much bigger number. Okay, so let's so the yes. Okay, and so I wrote this as 1.2 times 10 to the 6 joules. I could have also written it as 1,200 kilojoules. That's the same thing, okay? And I think this is probably they're probably looking for it in kilojoules, although this number this number is technically right. Moving on. All right, let's do another one. All right, I'm trying to go. Okay. All right, so we're going to be doing a lot of efficiency. Let's do another problem here. Let's skip ahead. Let's get something. Oh, how many calories does he burn during 8 hours of sleep? Okay, a sleeping 68 kilogram man has a metabolic power of 71 watts. Okay, we have not talked about watts. I think now is going to be a good time to talk about watts. Okay, but let's talk about you, a human being, and your body. Now, normally, well, all the time, okay, you use quite a bit of energy. Just me sitting here, or if you're sleeping, you're using metabolic energy. Your cells need a little bit of energy all the time. You have to do things like breathe, digest food, pump the blood through your body, move your muscles, whether you're sitting there or not, you have to breathe, right? Your lungs have to contract. And so a lot of the energy that you use just goes to basically keeping you alive. Okay. And so um, this guy uses 71 watts. Okay. Now, what is watts? Watt is something called power. Okay, and power is the amount of energy that you use per second. Okay, so let's write down some equations here. All right. All right, so let's talk about this. Um, Power is equal to energy used over some time period. Okay. So this is how much energy something costs as a function of time, right? Um, this is what you get charged for, right? You don't get charged for the like when the power company bills you, okay? They bill you by the power that you use, right? You pay for power, which is energy per second. And so this is going to have the units of, I'm going to draw these square brackets, which means unit. Okay, this is joules per second, or that is 1 watt. Okay, and we also need to talk about different forms of energy. So there's two main ones. There are joules, and there's also calories. Okay. Um, all right, let's look at another problem. All right. A sleeping 68 kilogram man has a metabolic power of 71 watts. Okay, so we need to find the conversion between joules and calories. All right, so let's check this out. Everything that you eat has energy in terms of this unit called calories. Okay, and we use calories for our food here. Okay, and there's a little bit of confusion because 1 calorie on a food label is actually equal to 1,000 calories, which we use in science and chemistry. Okay, so it's not really SI units. We use joules, but a lot of things are in calories, and so that's kind of the standard that we go with. Okay, so we need to write down this conversion here. So we're gonna say that 1 calorie with a big C is going to equal 1,000 actual calories, which is a little c. Remember, when you see this on your a food label, it's actually referring to kilocalories, which is the big C. We call it calories. I don't know why. All right. So this is equal to 4,190 joules or 4,190 kilojoules. All right, SI units or joules, that's what we're gonna go with, okay? And yes, if you look at the picture, you can actually burn food and release the energy that way. Okay, so you can burn it, that releases the energy, or you can digest it, which also turns it into chemical energy in your body. All right, let's go back to the problem. The problem says, how many calories do you burn during 8 hours of sleep? All right, so um, let's see. He burned 71 watts. Okay, that's the meta has a metabolic power of 71 watts. Okay, so that means that every second he's burning 71 joules per second. That's just to keep you alive, like life support in your brain and dream mode. Okay. All right, so the question is, how much did he burn? Yeah, how many calories did he burn in 8 hours of sleep? Okay, so we're gonna do this in joules first because I mean, who the heck works in calories. And then at the very end, we'll convert it into joules. All right, so here's what we do. We say 71 joules per second. This is our total energy. Okay, we know the rate that you're burning energy. This is how much it takes to keep you alive. Okay, for 8 hours. So that's 8 hours at 60 minutes per hour. Okay, so our hours are going to cancel. And then we have 60 seconds per minute. Okay, this is going to be the energy that we burn, and then we want to convert this into calories. So we're going to use this as a conversion factor. All right. So, what I'm going to do here is I'm going to say, all right, I'm going to take my equation here. I'm going to divide both sides by 4,190 joules, 4,190 joules. Okay, this just equals 1 over here. So I can multiply this by my conversion factor. And so I'm going to have 1,000 calories divided by 4,190 joules. Okay, so I'm doing this all in one thing here, right? We're gonna do it all in one shot. I'm gonna put all this in my calculator. Let's look at our units here. Okay. Let's make sure everything cancels. Okay, first of all, our hours are gonna cancel. Okay, hours are gonna cancel. Um, and our minutes are gonna cancel here. Okay, that's good. Then our seconds will cancel. So now we just have joules left. And then here, look, our joules are canceling, and so we're gonna have this in calories. We're gonna end up with calories. All right. So let's plug it in to our calculator. All right, I'm gonna okay, these are at different heights, and so you can't. All right, you know what, I'm gonna stop sharing this. It's too much, man. It's too much. All right, so here we go. You can see my can't see my calculator. Okay. Then you can't see the number. You know what? I'm just gonna enter it in here. I'm gonna read the page. All right. Imagine me typing into the calculator. So, okay, what? Okay, there we go. We can. We just need a different. There we go. The perfect angle. But now I can't see the screen. But that's okay. All right. So we had 71. Where did my numbers go? Oh, jeez, man. My desk is full of stuff. Okay. I need a smaller calculator. Okay. Anyways, you know what? All right, 71 times 8 times 60 times 60 times 1000 divided by 4190. Oh, jeez. All right, we're gonna check now. Did we enter everything in here? I think we did. All right, so we got our thousand, we got minutes, seconds, 8 hours, and 71 watts. And so the answer is, oh, that's a lot of calories. All right, let's write that down. Let's write that down. All right, so the total energy is going to be 488,019.0931 calories. Okay. And wow, that is way too many digits. Well, I'm going to convert it from calories to kilocalories. So I'm going to move my decimal place over here. That's one, two, three. So it's going to be 488 uh big C calories or kilocalories, and that is my total energy in kilocalories. Okay. And all this other stuff here. It doesn't matter. The answer is 488. Yes, 488, 490. That's a that's fine. All right. So what did we do in this one? We converted from joules, well, or from power, right? Watts per second, and then we converted that to calories. So we had to find this conversion factor here. Okay, we got to convert from calories to joules. This is your conversion factor. Okay. And then to move it over there, we moved our decimal place over three. That converted it to kilocalories. All right. I wasn't going to do this, but there was yeah, let's look at another problem. Okay. Because if you're watching this, it's probably because you want to see problems. So let's find another problem. Let's do it. Yeah, we're just gonna do it. All right. Oh, power. Each time he does one push-up, Jose, who has a mass of 89 kilograms, raises his center of mass 25 centimeters. He completes an impressive 150 push-ups in 5 minutes. No way. Okay, that's crazy. If we assume that lowering his body has no energetic cost, what is the metabolic power during this workout? Okay, I feel like we're missing some information here. I don't remember what. Okay, this probably, since I don't remember how to do this one, we should probably do this one. All right. In fact, it costs Jose a certain amount of energy to lower his body, about half of what it costs to raise it. If you include this in your calculation, what is his metabolic power? Okay, so they are looking for power. All right, it doesn't tell us a lot in this problem. So we're gonna need to look some stuff up in this problem, okay? Because right away I can tell that they're making this problem hard because they're leaving out a lot of information, which that's fine. We're gonna have to look some stuff up. That's okay. It's fine. We can do that. All right, we're gonna look up some stuff. All right, but first, let's write down what we do know. Okay, let's start a new problem here. The mass of Jose is 89. Wait, what? Who has a mass of 89 kilograms? Yes, for a moment, I was like, why does he weigh 89,000 grams? I was like, okay. Anyways. And let's see. Okay, so his center of mass, it raises by 25 centimeters, so not a lot. Okay, maybe like I don't know, 10 inches. Okay, that's pretty good. It's about a maybe a foot, a little less than a foot. Okay, and he does 150 push-ups. Push-ups. Okay, so I'm like, okay, now it's starting to make sense. And this takes him 5 minutes. 5 minutes. Okay. All right, I think I'm starting to get it now. So what happened was when I read this problem initially, I'm like, what the heck am I? What are we even supposed to calculate here? They didn't give us any data to work with. They didn't really tell us um what his metabolic rate is. Okay, but here's some things that we do know. Okay. We know that it's going to take a certain amount of energy to raise his center of mass. Okay, that is potential energy. Okay, so that's what we can say is if you raise your center of mass 25 centimeters, okay, that means your potential energy has increased. Okay, so that comes from the guy doing the push-ups. Okay, so he's lifting himself up. Okay, and we're gonna look at the average. Okay, so that tells us we know that he did 150 push-ups. Okay, and every time he does a push-up, his center of mass raises 25 centimeters. Okay, so we can get a number from that. The other thing that we do know, and they talk about this a lot in the chapter, is that human beings are 25% efficient. Okay, so that means, let's write that down. Human beings are 25% efficient. Now, if you do 150 push-ups, you are going to be super hot and super sweaty, okay? And so that means that 75% of the energy that your body had to use to do those push-ups just goes off into space, right? Your skin heats up, you're radiating infrared radiation, right? You're giving off heat. Air molecules are hitting your skin, they're absorbing your perspiration, and they're carrying away heat. All of that heat from your body goes into the room, right? Have you ever been around like in a really small room? Well, it starts to get hot because human beings, we radiate a lot of heat. If you're just sitting there, right? Just breathing, right? It takes, a certain amount of energy just to keep you alive. That whole time you're giving off heat. Okay? All right, so I think we can figure this out because we know humans are 25% efficient. All right. So first things first. Let's calculate the potential energy for one push-up. So see, how did we figure this problem out? Well, basically I wrote down everything that I know, right? What do you know? Write it down and then think about, all right, am I missing something? What do I need to look up something? For example, how many, I didn't remember how many calories were in a joule, right? I'm not that kind of physicist, right? Maybe a long time ago, you know, physicists just knew that like, okay, there's 4,190 joules, okay, in a calorie. Um, I am from the generation where I remember where to look things up like you. We don't actually memorize the information. What we memorize is where to look it up. And I know that in the PowerPoint slides, it tells you what the conversion factor is. Right, Zeus? Yeah. Oh, Zeus. Oh, you're so old. My cat's like almost 20 years old. He doesn't look old, but he is. Time is, it's been pretty good to Zeus. All right, Zeus. Can you sit over here with Pikachu? For a moment, Zeus. Okay. You sit over here. Yeah, okay. Zeus is gonna hang out here with me. All right, so let's calculate the energy in one push-up. All right. So when you do a push-up, here's our brotato. Okay, he's doing push-ups. Okay, and his center of mass, we'll say, is there. Okay, how much did it say? We wrote down, okay, this raises by 25 centimeters. Okay, so our height change here, delta H is 0.25 meters. All right, how much potential energy does he gain? Well, we know that it's mg times delta H. This is our potential energy. So for one push-up, okay, we're going to have 89 kilograms times 9.81 meters per second squared times our height, which is 0.25 centimeters. Okay, and this is, let's just write the whole thing out, man. Okay. I'm just gonna write all the numbers. I don't have time to keep writing this down. You probably don't want to see me write the same thing over and over. We're just gonna get all the energy here. Okay, so this is the potential energy. Let's just get this. We can, and then we can multiply this later. All right. All right, so what do we got? We have, we need to turn on our calculator. 89. Oh, we can go like this. Okay. 89 times 9.81. 9.81. Come on. All right, here we go. Calculator and there. Ooh, there, that's good. All right. Times 0.25. All right, that's gonna give us, does that seem right? Oh, geez, no, look what I did there. I did 25 meters. I'm like, wait, 21,000 joules? That seems a little high for one push-up. Okay. That's a little bit better. That is 218 joules, less than 1 calorie. Is that right? Oh wait, a calorie is 4,190 joules. Oh, that's not even a calorie. Oh, bro. Jeez. Yeah, so that's not maybe the best way to burn calories if you're trying to work out, but all right, it does build muscle. All right. So 218.27 joules. All right. So that is the potential energy for one push-up. All right. And now we want to find what, I don't even remember. What do we? Oh wait, I can look here on the screen. It's right here. What are we doing? Sometimes I don't even know. All right. What is his metabolic power during the workout? So, how much energy is he using per second to do these push-ups? We're looking at the whole average, and it took him 5 minutes. All right, let's find the time. Okay, so time is going to equal 5 minutes. Um, and there are 60 seconds per 1 minute. Okay, so see, I'm gonna find the time. So 5 times 6 is 30 plus that extra zero. That's 300 seconds. Okay, so the total time that he does push-ups is 300 seconds. Our minutes cancel out. Okay, the minutes cancel out. And so we have 300 seconds. Okay, and we know that human beings are we're only 25% efficient. All right, so let's find just the total energy. We'll get to the efficiency in a minute. Uno momento, por favor. All right, so he did the total energy, the potential total for all the push-ups. All the push-ups, 218.27 joules, and he did 150 push-ups. 150. Okay. So 218 times 150. Okay, so that's a fair amount of calories. Okay, and wow, you would be tired. Okay, so 32,740.875 joules. And again, I'm just writing this down for calculations, and In the end, we're going to round it all off. Okay. So that's the total energy in joules. And are we supposed to convert this into? I don't want to convert it to calories. Okay. So, and human beings are 25% efficient. Okay. So his total uh metabolic energy. Okay. And that's the total metabolic energy, and humans are 25% efficient. Okay. This equals 32, 32,740.875 joules. Oh, it's painful. It's painful to write all those decimals. Okay. All right. So we're going to do that. We're going to divide this by 0.25. Wait. All right. So that is 130,963.5 joules. All right. Now, the whole workout, okay? We want to find his metabolic power. That means how much energy per second, okay, per second is he using? That's the power. Okay, so that means we're going to take for power. Okay, power is going to equal his metabolic energy divided by the time. Okay, well, we got both of these now. So we have 130, 963.5 divided by the time, which we figured out is 300 seconds. Okay, so I'm going to divide. I really don't like doing this. I should have just all done it in one line. But man, if you mess this up, oof, good luck trying to figure that out. Oh, all right, we got a number for the power here. The power is 436 watts. 436.5 watts. Okay, because we had up here, this was joules. I'm gonna write the units in red. Joules per second. I put the seconds there. Okay, so this is what 436.5. Let's put in that number. All right, and so we have two significant digits. 400 and that's 440. We're gonna go with watts and submit it. Yes, we did it right. Okay. Last one, and then we're gonna call it good for tonight because it is almost midnight. All right. So, in fact, it costs Jose a certain amount of energy to lower his body, about half of what it causes to raise it. All right. So let's do a quick calculation. Okay. So, total energy then. So E up and plus E down is E total. Okay. We computed the energy going up. Okay, that is oh, this is our metabolic power. Okay. Let's do this. We're gonna find our energy and then divide it by time. Okay. So this is all right. So we had 130,163.5 plus that same number. Well, I guess we could have just multiplied it by 1.5, whatever. All right. So 130.1 or 130,163.5 divided by 2. Okay. And then we're going to get a number for that. We're going to divide it by time. And see, look at this. There's no way to go back. Okay, you know what? It's fine. I'm just gonna type in. We're gonna clear this mess. What do we got? 130,163.5 plus 130,163.5 divided by 2. That seems reasonable. All right, so that energy is 196,000. I just rounded off. And that's joules. I instinctively rounded it off. Maybe I wrote a six instead of a five, but you know what? I'm going to go with 196,000 joules. We're going to divide that by the time. Okay, we probably could have just multiplied our power by 1.5, but you know, we're going to do it the hard way because we're going to divide this number by 300. That's our time. Divided by 300, that gives us 650, which is essentially 440 times 1.5. We're gonna go with that. I kind of rounded off there, so let's see what it gives us. No, I think actually it's good. 650 watts. And the survey says we did it. Yeah, that's the right answer. Well, I typed in those numbers. They are definitely right. So, all right, we did some good conversion here. There's a lot of unit conversion going between uh converting between calories and joules, and then also finding the power. Power is the amount of energy that you are using per second. So you just sitting here to looking at the screen, yes, it takes energy, okay? Your body is working hard to keep you alive, pumping your blood, making you breathe, keeping you thinking. Your brain is uses up a lot of energy, okay? A lot of energy. In fact, that's why some people think that we became so smart because as we started growing food, like whenever that happened a long time ago, hey, we had more calories because we started cooking our food, right? If you cook food, you get way more calories out of the food than if you don't cook it. All of those extra calories basically gave us the ability to have time to sit around and think about stuff, right? And so our brains started to evolve, right? Apes and chimpanzees, they basically spend all of their time hunting and gathering. It takes a lot of energy. They're also vegetarians, and so they have to find a lot of plants to get all the calories that they need. Okay. Anyways, thanks for watching this video. There will be more videos about chapter 11. Also, we're going to do some chapter 12 videos too. Thanks for watching.
Thank you, like and subscribe down below.